Yes, it's true. Some soils do actually behave like a fluid under certain load conditions. Just like in February of 2011.
Now, a once vibrant city brought to its knees in what New Zealand's Prime Minister has called his country's darkest hour.
An earthquake of magnitude 6.3 struck the city of Christchurch, which is the biggest city in the southern island of New Zealand. This disaster resulted in 185 fatalities and several thousands more injured, making it the second deadliest natural disaster in New Zealand's history. A magnitude of 6.3 earthquake might seem low compared to other significantly bigger ones, like the Great Chilean Earthquake of 1960, which recorded a magnitude of up to 9.5 on a Richter scale. However, the Christchurch earthquake left the residents completely in disbelief. I mean, just imagine having to witness something like this. Your car almost completely buried in the ground, or your neighbor's house sinking just next to you. I don't know about you, but I know that personally I would be terrified to be in such a situation where everything around me is sinking on what was supposed to be solid ground.
How, Sway?
Let me take it from here, Sway. My name is Clemens, and in this video, we will explore about soil liquefaction, why and how it happens, and the solutions that geotechnical engineers implement to prevent soil liquefaction from happening. Welcome to Geotechs with Clemens. Soil liquefaction occurs when the effective stress or the shear strength of the soil is reduced to essentially zero. This may be initiated by either monotonic loading, meaning a single and a sudden occurrence in change in stress, or cyclic loading, meaning repeated changes in stress conditions, typically the forces induced by earthquake shaking. This loss of soil strength leads to the ground to behave like a viscous or in a fluid-like state. However, this phenomenon does not occur in all soils. Special conditions have to be satisfied, for example, the type and the nature of the load that the ground is being subjected to, and the characteristics of the ground soil. Saturated sand and silty sand soil are prone to liquefaction. These ground conditions are usually found in areas with high water table or in areas that are near the coast. Unlike clay soils, which are cohesive in nature, that they require higher forces to separate their electrochemical bonds. Sands, on the other hand, are classified as cohesionless or non-cohesive soils, meaning that their particles do not chemically bond or stick together. Because of the lack of these cementitious characteristics, sandy soils have larger voids in between their particles that water can occupy, making sandy soils more susceptible to liquefaction.
What do you mean by that?
You see, during an earthquake event, for example, there is a release of tremendous energy and a subsequent shock wave in the Earth's crust. As the S wave, a component of the earthquake, propagates through the soil, forces are exerted on the particles, leading to soil compression. In response to this soil compression, the water trapped between the soil particles is squeezed and the pore water pressure increases. The water will obviously attempt to flow out from the soil to zones of low pressure, usually upwards towards the ground surface. However, suppose the loading is rapidly applied and is large enough or is repeated many times, just like in the event of an earthquake, and at the same time, the water does not flow out before the next cycle of loading is applied. In that case, the water pressure will build up to the extent that it exceeds the contact forces between the grains. Now, this is a problem because the weight of the buildings and the overlying soil layers is transferred from the ground surface to the layers of the soils or hard rock at greater depth via these soil particle interactions. This loss of soil structure is what happened in the Christchurch earthquake event, leading the ground to behave like quicksand. There are other high-profile cases of soil liquefaction, like the 2018 Palu devastating earthquake in Indonesia. The ground lost all its strength and started flowing downslope, carrying everything in its wake and leaving the road in a buoyant-like suspended state. Geotechnical engineering solutions can be implemented to reduce the effects or prevent ground from soil liquefaction. There are many ways that this can be achieved. It goes without saying, however, identifying and avoiding construction on liquefaction-susceptible soils is the first measure. This can be achieved by characterizing the soil at a particular building site according to various criteria, such as the grain size, the density of the soil, the water table depth, and checking the seismic history of that area. Once the soil has been identified to be at risk of liquefaction, some foundation elements can be added to the infrastructure to minimize the effects. Soil liquefaction effects can be in the form of differential settlement, lateral spreading, and the loss of bearing capacity. Depending on the construction budget, foundation elements like piles, caissons, mat foundation, and ground anchors can be installed. Improving the strength, the density, and the drainage characteristics of the soil using various soil improvement techniques is another popular and cost-effective solution. This can be in the form of soil compaction, densification, grouting, using different drainage techniques, reinforcement, and stabilization to reduce the void spaces and strengthen the overall bearing capacity. The research in soil liquefaction is still ongoing, both in academia and in various construction institutes. With new technologies rolling out, it will increasingly become easier to identify, mitigate, and design for soil liquefaction to protect the infrastructure around us and save lives. I've been your host, Clemens, and if you enjoyed this video, please leave a like and subscribe to the channel. You might as well go and check out my previous video on why buildings sink. Until next time, cheers.